let's make a few comments about relativity and what we're interested in, classical relativity actually, or Galilean relativity in our case. Galilean relativity is basically composition of velocities, but there's something more profound which is more interesting from our point of view. And this is a question that we were seeing, or we will see when we discuss the problem of the concept of forces, and in particular the concept of inertia, of the first law of Newton that comes already from Galileo. And this was the question also about the rotation of the Earth. How do you have any evidence the Earth is not rotating? In fact, you have kind of common sense evidence on the contrary, because if I take a ball and I throw it upwards, if the Earth was moving, the ball will fall behind the Earth. And we don't observe that. We observe that the object comes up and down. So common sense says the Earth is not moving. So that was another of the problems that Galileo and actually all the heliocentricists and Copernicus found in presenting their theory and going forward. There was no experimental evidence that this was indeed the fact, that the Earth was not at the center, the Sun was at the center and the Earth was rotating, right? There's something even more profound, is that you could always say that the Earth rotates around the Sun, or the Sun rotates around the Earth, because motion is relative. So you could always use any point of view to describe it, and so in that case, Ptolemaic and Copernican models will be okay. The problem is, of course, one is more convenient because it's much more simpler, and we were discussing about that in chapter 1. Frame of reference selection is arbitrary, but there's some that are much more functional than others, right? So there's this, we're going to be discussing is the principle of relativity, and I think that's the single example that we want to analyze, is the idea of, well, we saw at the beginning of chapter 1 on the language of motion that you're in the station, and then, or you are sitting on the train, and your friend is out there saying you goodbye, right? So let's maybe make a small diagram of this scenario, right? So someone is on the train or on a car, right, on the window, and then someone is on the station. And then let's say that there is an apple, right? And the guy throws the apple. And let's imagine, by the way, that the train is moving with velocity v, right, horizontal. Let's make it one-dimensional. There's nothing to gain here by making this more complicated. Okay, so now we have the object moving in one dimension with a certain velocity. So the question is, we want to analyze, right, too many, the motion of the apple, right? So the apple is going to be thrown upwards, and we're going to see what's happening. So in motion, we said motion is the change in position of one object in time with respect to another one. That another one is the one that's defining our point of view of, as we say, the frame of reference. So we have two ways in which we can describe this motion. We can describe the motion from the point of view of, let's say this is Bob, or we can describe it from the point of view of Alice. Very good. So let's start from the point of view of Bob. Bob is sitting on the train or standing, it doesn't matter, the train is moving with constant velocity, and Bob asks, okay, is the apple with respect to myself, right? So we could draw Bob, and then we can make in Bob's hand actually an axis of coordinates. This is y, right? And this will be 0. And we're asking what happens with the apple, right? The apple is here. So the apple is going to go up, and it's going to come down, right? So from the point of view of Bob, horizontal motion, by the way, we're concerned here about the horizontal motion. Why? Because if I throw the apple up, and I ask Alice, was the apple going up? Alice is going to say yes. But if I say, was the apple moving? Alice is going to say yes, but I'm going to say no. And let's see how. If I drop the apple up, or I throw the apple upwards, I wait, the apple falls down. So what is the velocity of the apple in Bob's system? And obviously we're talking always about the velocity of the apple. So let's say the velocity of apple in Bob's system, and we're talking about the horizontal, always. This is just the horizontal component of the velocity. So does it change position? Is the initial position and the final position different for Bob horizontally? No, the apple just goes up and down. So the initial position horizontally is 0, the final position horizontally is 0, the displacement is 0, and if the displacement is 0, velocity, even if you wish to average velocity, which is change of position in time, is of course going to be 0. So does the apple have, for Bob, frame and axis of coordinates, any horizontal motion? Doesn't. But what about Alice? Well, for Alice, frame of reference, she's going to put her frame of reference, let's say even if you wish, in her hand. But what she's going to see is that Bob threw the apple here, so let's just draw the apple, right? So Bob is going to throw the apple upwards. And what she's going to see is that the apple is going to go up, but it's going to do this. And it's going to fall down in Bob's hand, because of course, the apple falls for Bob in his hand and for Alice in his hand, because otherwise it will be not the same. It will not be the same phenomena, and we're used to studying the same phenomena. So the apple certainly is thrown and falls in Bob's hand for Bob, but it's also thrown and falls in Bob's hand for Alice, right? It doesn't fall anywhere else, because then that will be weird, right? That will be inconsistent. So thanks God, reality is consistent, so we can use physics. So the apple is going to do some sort of parabolic motion. Why it's going to go up, but it's going to be horizontal. So what is the change in position of the apple for Alice? Well, the change in position, of course, is not going to be non-zero, because the final position this train is moving. So after some time, the train was here. After some time, the train is going to be there, and the apple with the train, right? So this position is different from this one. So now delta x is non-zero. So velocity, which is delta x over delta t, is going to be non-zero. That is, velocity of the apple in Alice is going to be non-zero. Now let's put some numbers here. Let's say the train is moving 5 miles per hour, or 5 meters per second. Let's use meters so we avoid any issues. And the observation lasts 1 second, right? From here to another instant of time, let's say when you're here with the apple already in your hand again, right? Has moved here, the train. And that's what you are analyzing and what she is analyzing. From your frame of reference, this is the same as saying displacement is 0 and time is 1 second. This is 0 meters per second. That's, so you ask what is the velocity of the apple for Bob, it's going to be 0 meters per second. If we ask what is the velocity of the apple for Alice, it's going to be the displacement, and in this case the displacement is, well, where does it go? Well, the train has moved how much? 5 meters per second. So what she is going to observe is that the apple was at 0, right? The apple was at 0, and at some and 1 second later it's going to be at 5 meters. So what is the displacement? That's going to be, the displacement is going to be, that's going to be non-zero. The displacement is going to be how much? So it's going to be 5, which is that position, this position in Alice's reference frame, minus the initial position, which is 0, which is 5 meters. And so what's going to happen with the velocity? Well, it's going to be 5 meters divided by 1 second, so that's going to be 5 meters per second. And here we go back to the discussion we had at the beginning of the course when we said, let's analyze motion, and we said there's ambiguity in motion. Why there's ambiguity? Let's come here. For Bob, the apple has 0 meters per second, not moving. And again, I remind you this is only horizontal. For Alice, right, this is the point of view. For Alice, the apple for Alice is moving with 5 meters per second. Yes, it moves. We have an ambiguity. How do we solve this? Well, Galileo solved this problem, and it's actually the solution for the problem of the apple being thrown if the Earth is moving, because the train becomes the Earth, and so we can answer that question. But at that time they didn't know. So let's see what's going to happen with the solution. So is there any way that we can make this compatible? And the answer is yes. We can see, and we can plot that from Alice, we're going to have a frame of reference that we can call, again, let's use prime, right? And there's going to be another frame of reference. There's going to be Bob's, right, which is x and y. And so the apple in Bob's is not moving. The apple in Alice is moving. So Alice is going to see that there's going to be a change in the x position. Bob is not going to see any change in position. Why is that? Because this is in the hand of Bob. It's moving with the train. So what we're observing is that Bob, frame of reference, is moving with respect to Alice's frame of reference. And so we can define that there is a velocity, this goes with what velocity, by the way? The velocity of the train, which is 5 meters per second. So we can see that the frame of reference of Bob is moving with respect to the frame of reference of Alice. And if we want to trace that, we have to see that the velocity of the apple in Alice, and now I'm going to make it vertical so hopefully it makes more sense, is going to be, is going to be what? The velocity of the apple in Bob plus the velocity of Bob in Alice. And if I do this, what's the velocity of the apple in Bob? That's 0 meters per second. What's the velocity of Bob, the entire frame of reference moving with respect to Alice? 5 meters per second. So what is the total velocity of the apple in Alice's system? 5 meters per second, which is exactly what she observes. Now let's see it reversed. Before we analyze how can we describe the velocity of the apple in Bob, of course we can see mathematically directly, by the way, that we said that the velocity of the apple in Alice is just simply the velocity of the apple in Bob plus the velocity of Bob in Alice. So if in fact I want to solve for the velocity of the apple in Bob, I can just take this here, subtract it, and so I'm going to see immediately that this is the velocity of apple in Bob, is the velocity of the apple in Alice, minus the velocity of Bob in Alice. Velocity of apple in Alice minus velocity of Bob in Alice. Now this is not as nice as this one because it looks like this and it's going diagonal, right? So there's something here not working. What is the velocity of Bob in Alice? This is a critical thing. Say that you are standing on the station and the train is coming. You can do this with a pencil, right? Just move it from one side to the other. Let's say like this, you take it on the left hand and go towards your right hand, right? And say, what is the direction of this motion? Let's say it's moving 1 meter per second, it doesn't matter. What's the direction? Well, it's going from the left towards the right, left towards the right. So if I describe this as the positive direction, this is going with what? With plus 1 meter per second. But I ask you from your perspective, or if you turn yourself and look at this, how is this going? This is not going from left to right. For you might actually be going, and the recording is mirrored, so this is now messed up, but basically put it in front of you and you say it goes from left to right. Turn yourself around, do the same thing. And how does it go? It doesn't go from left to right. It goes from right to left. And then I'm not going from the negatives to the positive in my axis of coordinates. If I invert the axis of coordinate, the motion still happens like this, but now I have defined a new axis of coordinates. This is x sub 0 and this is x sub 2, where my x positive is looking here. So the object actually is moving with negative velocity. So when I invert the axis of reference, I have to account for a negative sign that inverts it. This is expressed that Bob in Alice, the velocity of Bob with respect to Alice is equal to negative the velocity of Alice with respect to Bob. If I'm standing in the station and the train comes and I define going north, which let's say that direction is north, and the train is coming north, I say, oh, the train is moving with 5 meters per second north. If the other guy is sitting on the train and looks at the station, the other guy sees me coming from the north to the south. You see the train going like this, but they see you going in the opposite direction. That's the sign in here. Your system with respect to them is just inverted. It just has a minus, which is exactly this minus over here. So then we could actually go back and say that the velocity of the apple in Bob is indeed the velocity of the apple in Alice plus the velocity of Alice in Bob. It just so happens that the velocity of Alice in Bob is exactly the same as the Bob in Alice, but with a minus. And then you recover that, and then we can indeed substitute and see that the velocity of the apple in Bob is the velocity of the apple in Alice, which we saw is 5 meters per second, plus the velocity of Alice in Bob. What is the velocity of Alice for Bob? Bob was going with 5 meters per second. He was moving like this. But for Bob, Alice is coming from here and moving towards there. And she's moving exactly with 5 meters per second, but negative. So this is going to be minus 5 meters per second. And so how much is that? That's 0 meters per second. How much did Bob registered 0 meters per second. The apple is not moving. And now we see something beautiful, which is sometimes enunciated as the principle of relativity, which is the laws of motion, but in reality the laws of physics are independent of the frame of reference. We can convert between different frame of reference. We have eliminated any ambiguity. It's just important to distinguish when I'm describing one frame of reference or another. But once I know the frame of reference and I know the motion of that frame of reference with respect to my motion, then I just need to add the velocities, where we do it like this, account for the indices, subscripts, right? It's not the same as saying apple in Bob, apple in Alice, or Bob in apple, or whatever you want to think of, right? You can come up with whichever frame of reference you want. Just think physically what that means and imagine how things are moving from that point of view, figure out the numbers, and you can then add them together with the right sign. So classical relativity, as we've seen, is just basically the composition of velocities. And we're going to have an object that is moving in a medium that is moving with respect to another one, right? And so we're going to always find two frames of reference. If we're talking about an airplane, one frame of reference is going to be the air, and the other one is going to be the ground. And if we're talking about, excuse me, for instance, and if we're talking about the boat on the river, one frame of reference is going to be the water on the river, and another frame of reference is going to be the ground. So it's very easy to understand that, for instance, if we're on the ground, we're always in the same position. So how do we understand this idea of being a frame of reference on the air if the air is blowing? Well, from the point of view of the air is not going to be moving. And from the point of view of the river, which is to say on the frame of reference of the river is actually not moving, because no object has a velocity with respect to itself. We saw this in the discussion about not existence of absolute space, right? If we only have one object on the entire universe, one single point, then it's impossible to describe position, size, velocity, or anything like that, right? So basically, if you want to think about that, imagine that the idea there is just like you drop a small probe or something like that, some small object, and then you're going to define your frame of reference in that object. And so if you have a river, and the river is flowing, let's say, this way, then you can just take a small portion of the water, so to speak, like a few molecules of those, or one molecule of that, and then define your frame of reference with respect to that molecule. That molecule with respect to the ground is going to be moving. But from the point of view of the molecule, actually it's the ground that is moving, because then that becomes equivalent to actually considering a train. If you're on the train, you don't see yourself moving, you see the station moving, and it's actually moving in the opposite direction. So it's important also to see why velocities are relative, right? The motion is always relative. It's relative to the second object with respect to which we are defining it, right? So we said motion is the change in position in time of an object with respect to another one. So that second object is typically, if we say that motion of this, of the water is the object that we're interested in describing with respect to another object. What's the other object? Let's say a small rock or something on the ground. But I also need to define a point here. And then conversely, I could say that I can analyze how this point in the ground, this rock or something, is moving with respect to a molecule in the river, a molecule of air, right? That I'm taking that as my reference frame. That's the object I'm taking as a reference frame, right? So then we can say that if from the point of view of the ground, it is the river that's moving, but from the point of view of the molecule of water, this point in the river is not moving, the ground is moving. How is the ground moving? In the opposite direction. That's why we said that any, if we use W for water, and we use S for shore, and then we use, we'll just keep it for the time being like that, we can say that then the velocity of the water with respect to the shore, it's equal to the velocity of the shore with respect to the water, but they're just negative sign. And this is what we were just discussing. If you have the train coming, the train, if you're sitting on the station, comes from the left to the right, but if you're sitting on the train, you see the station coming from the right to the left. And you can do yourself again at home, take a pencil and say it moving in this direction, turn yourself, repeat the motion, and actually you describe it the opposite way, going from left to right, then it goes from right to left, or the other way. And so we need a minus sign here to convert that. That's the first thing. And the other one is that any object that we define in one system is going to be definable in another. So let's take now a boat in the river, right? And then say what describes the velocity of the boat. So the velocity of the boat can be described in either one of these frame of reference, right? So we have this frame of reference of point of view, and we're now considering an object that is the boat. We could consider the boat our reference as well, and then describe the motion of the river and the motion of the ground with respect to the boat. But in this case, you just decided this. But you can repeat the entire thing, think from the point of view of the boat. So now this is going to be the object. These are the frame of reference. This is the object we want to describe. So the question is going to be, well, how do we describe the object onto the frame of reference of the shore, right? And we typically use this notation where we first describe the object we're trying to describe the motion, define the object we're trying to describe the motion, and then with respect to what? To our frame of reference, right? And so we have that we write first boat is the object, S is frame of reference. And then the velocity of the boat on the shore is going to be equal to what? The velocity of the boat on water plus the velocity of the water on the shore. And we use this mnemonic or mnemotechnic rule that we say that in diagonal this cancels, so we have both shore as we expect. And this is pretty much composition of velocities. That's all there is. But again, the critical point to actually see these things is imagine that you are defining a frame of reference as in a molecule, just a point in the river. The river is flowing, yeah, but that's just with respect to the ground, with respect to which we typically define everything. But if you were out sailing, or if you're in the train, or if you're in the airplane, you don't see yourself moving. I mean, we understand in our day-to-day speaking that we are the ones moving and the Earth is not moving with respect to us. But motion, again, is relative. There's no absolute space. So once we get rid of that prejudice that comes from our experience, we train our intuition to understand motion is relative, and so I need to define what's the object I'm defining the motion for, and also with respect to what point of view I'm defining it. And so we can take a molecule of air, we can take a molecule of the river and say, well, with respect to this point, it is the other things that are moving, right? There are the other things that are moving with respect to me. It's not that I am moving, it's that they're moving, because of course the velocity of the river with respect to the river is 0. No object has velocity with respect to itself. That will be kind of a contradiction in terminis, right? So that doesn't make sense. So that's what we're gonna see. So for problem number 2, we're gonna have a boat, and the boat is trying to cover a distance north with respect to ground, right? Why ground? Because north is gonna be signed by the North Pole, so which is gonna be the Earth. So then there's the river which is flowing, and the river is flowing with a velocity of we could say minus 1.2 meters per second if you wish, right? And then we're gonna have a velocity of the boat, which is the velocity of the boat. If you are in the boat and you check your speedometer, right? It's like being in your car and you check your speedometer. That's gonna be 1.85 meters per second. Now it's important to identify this information with respect to which frame of reference is given. Now, if we make a diagram of the situation where we have here is like we have the ground, and then we have the river, and then we want to reach from this position to this position. So what we actually want to do is do this. But there is a problem that the river is pushing this way. So if the boat were to travel just due north, then we're going to end up going towards the left. It's going to be carried by the flow of the river and end up in a different position. And I just want to go from, let's say, P1 to P2, right? These are the positions, not x as in x horizontal axis. So P1 to P2, and if I go with this, then I'm gonna, with the river flowing in this way, it's gonna go that way, right? So what I need to do is just do courses not north. I need to compensate for that. How much do I need to compensate horizontally? Well, you have to compensate exactly the same amount that the river is pushing. So one way of seeing this is that you're gonna have the river flowing in here, so I need to do course in here. How do I know that? Well, because I'm going to take opposite, right? If the river is flowing in minus 1.2, I'm going to have to go in minus the velocity of the river. So minus vector is just simply tilting the vector. And at that point, it's going to become obvious, right, that then I can write this is going to be minus velocity of the river. At that point, becomes obvious that this vector or the negative of that vector is just simply the sum of, I can invert this one and then I have the sum of those, right? Which is to say, if we write the composition or the law of the compositions, we're going to see it immediately. How much is this velocity? Well, that's the velocity of the boat with respect to the ground, right? And how much is the velocity, let's say, shore, right? And how much is this velocity? Well, that's the velocity of the water with respect to the ground. So then we see that the velocity of the water with respect to the shore is minus 1.2 meters per second. The velocity of the boat with respect to the ground, with respect to the, that's going to be with respect to the water, not with respect to the ground, with respect to the water. That is the velocity with respect to the ground. So if we're going to see that the velocity of the boat with respect to the water is going to be that, which is the modulus of that, it's going to be 1.85. And then the velocity of the boat with respect to the shore is just going to be purely vertical, which is what we want to achieve, right? Just purely north. So this velocity is obviously going to be 0 component in x. There's no motion in x, and it's going to be purely just the y component, whatever that is, right? Okay, so the question is, how do we define exactly this angle theta? Well, we can just simply use SOHCAHTOA. That's just a very easy way to do it, and see that this is the opposite, so I need to use the sine. So sine of theta is going to be opposite, which is the velocity of the river, modulus, divided by the hypotenuse, and the hypotenuse is the velocity of the boat. How much is the velocity of the boat? 185. And if you make that and you solve for the angle, you're going to find that the angle is 40.4 degrees. So this is just geometrically. Again, we see vectors, then it's trivial. If we see this thing is trivial because I just need to go north, but the river is pushing left, therefore I need to go this way. How much? Well, you need to go enough such as the component, the horizontal component of this is 0. How do you achieve 0 component on the shore? If the boat has, with respect to the water, the opposite velocity. So basically this is you on a automatic stairs, right? And then you're just walking in the opposite direction of the stairs. Stairs coming down, and then you're going up. If you go up as fast as the stairs go down, then you're always in the same position. That's kind of what we're seeing over here, right? If we want to not change our horizontal component, we need to have a horizontal component that it's opposite of the velocity of the medium, or the velocity of the stairs in the example of the stairs. And that's what pretty much we're saying over here. We need to have 0, so the only way to have 0, because this velocity is actually 1.2 if you wish 0, right? So the only way is that this has an x component that it's actually the opposite, so it needs to have an x component of 1.2 positive, right? And then how much is going to be the y? The y is going to be what, well, the y is exactly what we want to find, it's just Vs in y. And so the question is, how much is this? Well, you can figure it out, because that's going to be the same. This square plus that plus this square, it needs to be this square, which gives us Pythagoras. But instead of doing that, we can just use the vectors and find it out immediately. So again, we can compose the velocities, and then we're going to see that, or we can just simply analyze the angles and see it. This is a particular example where using the angles and using basic vectors solves the problem easily. We're going to see another one, and then we're going to see one where using composition of velocities is much more convenient. Okay, so let's pretend that we actually didn't know any trigonometry, right? And that we're trying to figure out what's the angle in here. What's going to be the angle? Well, we know that there's a velocity this way, so we know this still applies. But well, let's use the formal composition of velocities. What information do we have? We have the velocity of the river, but the velocity of the river is not with respect to the molecule of water, it's with respect to the molecule of dust or the rock that we have on the ground. So then the velocity of the river, of course, is just defined as the velocity of the water with respect to the shore. And then we can define this as a vector and say it has x and y components. What's the x component? Minus 1.2. What's the y component? 0. The river is just flowing horizontally, right? So this is the first realization. So we have the first point, the first information. What's the second information? The second information is the velocity of the boat. But what is this velocity? This is the velocity the boat is reading on his speedometer, right? The guy sailing, it's reading on the speedometer somehow. So how is measurement of, and this is why we need to actually understand the physics, right? On problems, and not just simply use mathematics. We need to be able to identify the pieces of information. When we say the velocity of the boat, when we say the velocity of a car, when we say the velocity of the airplane, how are we measuring that velocity? We'll see this more obviously in, or more specifically actually on fluids chapter after the first midterm, and chapters later. So the velocity of the river or the velocity of the boat traditionally use knots, because they would take a string or a cord and then tie some knots and space them equally, and then you throw it and they calculate how many knots in an amount of time, right? That was the kind of velocity. And if you take the velocity of the airplane is using a tube that we will see a Venturi effect to actually compute how fast you're going with respect to the air. So important thing here, if you're taking knots and I'm throwing them, I'm moving with respect to the water. So this velocity is going to be the velocity of the boat with respect to the water. And if I'm on the road, I'm measuring my velocity with respect to the road. If the road was, imagine it's like a huge boat, like a petrol boat or one of those large containers, boats, and I'm moving myself, I'm measuring my velocity with respect to the deck of the boat, but the boat might be moving. So then it's not the velocity with respect to the ground, even though we're used to think it's with respect to the ground. That's just simply because we're just always with respect to the ground. We're not, the rod is not moving with respect to the ground. But in this case, the medium is moving with respect to the ground. So this is not the velocity of the boat with respect to the ground. This is the velocity of the boat with respect to the water. And so that's, right, it's actually going to be the velocity of the boat with respect to the water. Now, important thing, this is a velocity that we know is just the modulus. Why? Because this needs to go in diagonal. The boat needs to go diagonal to be able to compensate for the river. So of course this is going to be just the modulus. So we know that's 1/85. Okay, so we can just say that the velocity of the boat is the velocity of the river. And so we can use now composition of velocities. What we want to find is the velocity on the shore is what? Well, I want the velocity on the shore to have no horizontal component and have purely vertical component, right? So we can just call this v sub y. And remember, v sub y is just only the velocity, the y component of the boat on the shore, with respect to the shore. So if we add them together, of course, we use v sub s is equal to v, the boat, with respect to the water, plus the water with respect to the boat. And so this we can write then that the velocity of the boat with respect to the water in vector is going to be what? And here we can force ourselves to do that. This is what we were discussing a second ago. The velocity, the x component, is going to have to be the river positive, so it's 1.2. The y, I don't know, so let's just keep that bsy. So just then we can call this actually bsy, and this is going to be bw. So it's boat on water, the y component, right? So if I use Pythagoras, then from here I know that this is velocity of the river and this is velocity of the shore, and then I could try to find out, and I know that the hypotenuse is 185, so I could just solve for the velocity of y, and then I just got it, right? So how do we do that? Let's go for that. So bs, this is going to be 0, boat on the shore, y, equals to boat on the water, which is going to be 1.2, and boat in water, y component, plus the river. The river is minus 1.2 and 0. Actually, we could even not identify that information at this point. Let's call just this. So you will see where it comes from. The velocity of the boat with respect to the water, the x component. So this is the velocity of the boat with respect to the water, the x component. Now I put this together. And so what we're going to find is that 0 vsy, it's equal to bwx minus 1.2, comma, that's the x component, and the y component is going to be b water y plus 0, so that's 0. And so I can distribute it here between the horizontal and vertical component. Horizontal is 0 equals to b water x minus 1.2, therefore bwx is 1.2. So this is what we were just saying before. If I want to know what was the horizontal, well, the horizontal needs to compensate, because I know. So if you identify, you go directly, otherwise you just solve it this way. What about the other one? Well, we know that the velocity in the shore, with respect to y, needs to be equal to what? It needs to be equal to just directly the velocity of the water in y. And this is actually what we were just discussing before. How much is the vertical component of this vector? Well, that is actually just the velocity of the shore. The vertical component of this vector, which is this component over here, needs to be the same as the vertical component of this vector. And the horizontal component of this vector needs to be the same as this one, which is negative of the water, of the velocity of the river, right, on the ground. So from here then we can just use Pythagoras. Let's do it over here. So what do we know? That the hypotenuse of that, which is the velocity of water, right, this is equal to 185, which is equal to the square root of what? Of the bwx squared plus bwy squared. And so we just can find that it's going to be 1.85 squared. It's equal to 1.2 squared plus, and then we just don't know that one, so let's keep it that way, bwy component squared. So we can do 185 squared minus 1.2 squared, and that square root of that, that's going to be bwy. And now we're going to have two solutions, of course. One is going to be positive, one is going to be negative, but obviously we're using the positive solution. Why? Because it's the vertical component, the one, and it's pointing up, it's not pointing down. Otherwise the boat would just hit the ground, right? So that makes a lot of sense. So then we can make this calculation, and it's 1.4, about 1.4, and then that's going to be the y component. So now I ask, what's the theta? So now I know that this is going to be 1.4 and this is 1.2. So now I can use what is the direction of this vector, which is this one over here. Well, that direction is going to be what? I can use this the SOHCAHTOA, so I could use the tangent of theta. It's actually equal to what? Opposite divided by adjacent. So what's the opposite? 1.2. What's the adjacent? 1.4. And so what's going to be solving for the angle then? Theta, it's equal. That's going to be 0.78. And if you actually put it in degrees, you're going to see that this is 40.4, no? 40.6, that doesn't matter, right? Let's say 40.4 degrees. Well, how much is the solution? Well, it's exactly the same thing we just said before. But you realize that we just did the entire composition formally to find out that we need to have the components and divide the components to find the direction. Whereas if we just use basic trigonometry, we're going to see that the vector needs to be, the horizontal component of the boat needs to be opposite to the river. And so immediately I see that this is SOHCAHTOA. I know that hypotenuse, I know this, I can use the sign and solve it. So formally composing velocities, you can figure it out. It's just much more elaborated. In this case, it's just better to use trigonometry. If you're not that confident with trigonometry, then just do it formally. This is a particular case when doing it formally doesn't really add anything. Let's see another example based on this, which is problem 3. So in this new problem 3, it's basically the same information. It's the same situation. The river is moving 1.2 and the boat is moving 1.85. But now it tells us that the boat is moving 1.85 and it's directly going across. So it's basically going perpendicular to the river. So that means that we can start identifying information if we want to have what's the velocity of the boat or the water with respect to the shore. That hasn't changed. That's just, of course, minus 1.20. But now we ask what's the velocity of the boat with respect to the water. And before, excuse me, we knew that we had x and y components. Now the velocity of the boat in water is just simply going to be vertical, right? So then we're going to know it's going to have 0 component in here, and it's going to have the wy component. How much is that component? Well, the boat only has 185, so actually that's just simply 0, 185. Let me just, excuse me, that's just obvious from there. And then the question is, what is the velocity, magnitude and direction of the boat relative to the shore? So this is the velocity of the boat with respect to the shore. How much is that? Well, we can use composition of velocities. And composition of velocities, shore velocity of water plus the velocity of the water with respect to the shore. Now notice we're using the water and the shore because they're trivial, but you could even imagine we could make this as complicated as we like, and we could say like, oh, what about if there's now like a balloon just floating around, right? I can then make a new frame of reference, and you could just describe the boat with respect to the balloon and the balloon with respect to the shore. It just seems to be very inconvenient because how do you measure the velocity of the boat with respect to the balloon? We have no information in here, right? But sometimes you do have information. You can use intermediate steps, and we'll see that soon in another example. Other times just trivial. And now we can replace here, right? That's going to be what we were discussing before, the x and the velocity of the So it's going to be negative 1.2. That shouldn't be there. Negative 1.2 and 185. Just add in the vector. So then I can just see that the x and y components. So if I want to find what's the modulus of Bs, that's going to be 1.2 squared, negative 1.2 squared, plus 1.85 squared, and then the square root of that. And that's going to be 2.2. And then we can just see the direction theta, we could just say tangent of theta is going to be y over x. Before we do that, however, it's important to see. Typically we define this as the y component divided by the x component. But why is that? Because if we take a triangle, we're saying this is the y component, let's call this vector u, that's going to be u sub y, and this is going to be u sub x. And then we say the magnitude is just this, and the direction is just simply given as the tangent of theta, which is u sub y over u sub x. However, is this the situation? Are we defining that theta, as we do with this formula, as the elevation over the horizontal axis? Let's make the diagram of the motion of the river, right, of the boat. Now we say we have the shore, we have the boat, but the boat is just moving with respect to the water directly like this. And then the river has this velocity. So what's the total velocity with respect to the ground? It's just going to be the resultant, right? So this is the velocity of the boat with respect to the shore, this is the velocity of the boat with respect to the water, and this is the velocity of the water with respect to the shore. And that's why when I add this plus this, I obtain this, which is graphically obvious. And now this is theta. Now this is not the elevation over the x angle, over the horizontal, excuse me, x direction, over the horizontal. Now this is kind of the elevation over the vertical one. So in reality, if I use this formula, what I'm defining is not that one, I'm defining the complementary triangle, which is this one. So I will be finding this angle over here. So if you realize that, then don't use tangent. Then you realize what's the angle, and then you can do the inverse. Instead of doing y over x, in this case the opposite is SOHCAHTOA. So what's the opposite? Well, the opposite is this one. And what's the adjacent? This one. So actually, if I want to describe the direction as this theta, then I can just see that theta, I'm going to call this angle alpha, right? Let's call that angle alpha, and this is theta. So theta, according to this definition, or let's start, typically we define alpha, and then we say that the tangent of alpha, it's equal to what? Opposite, which, yes, this will be velocity of the boat in water divided by, or the boat, excuse me, in the shore, the y component, divided by the adjacent, so SOHCAHTOA. So adjacent, the adjacent of this alpha angle is going to be what? The x component of velocity of the boat on s. So that's going to be the velocity x component of the boat in s. And if I do that, then I'm just going to find that this is 0, I can find that the angle is 0.995 radians, which is actually 57 degrees. Okay? Again, I'm defining alpha, it's not theta, it's this alpha over here. So I could answer with that, but be careful, because that doesn't mean anymore the direction, the elevation over the horizontal axis. According to your calculation, that does not represent the elevation with respect to the horizontal axis. It represents actually, represents the elevation with the horizontal axis. That does not describe the velocity. If you want to do that, then you would have to say that the elevation is all the way up to 57 from here. So how much is this 180? You would have to say 180 minus 57, and that's going to give you 123, something like that. Correct, 123 degrees. You have to convert. Other option is just to realize that you have this diagram and immediately see how much is theta. Well, we can do it over here. How much is theta? Theta is given by, or the tangent of theta. So the tangent of theta is what? Opposite divided by adjacent. So what's the opposite of this theta angle? The theta is the WS, if you wish. And what's the adjacent? W water. Or, and then you just write water shore, and here you write BS, and then what's that? Well, water shore was 1.2. Excuse me, that's BW. Sorry. That's 1.2, and how much is that? That's 185. And if you do these numbers, then you are going to end up finding indeed that this is 33 degrees. And notice the 33 degrees plus 57, that makes 90, which makes sense. It's 57 plus 33, you have 90, which is a rectangle. So another example, excuse me, where you can see the math, but you have to make sense of the math if you use formulae. Otherwise, it's much simpler. Just realize that you have this and this, and then you have hypotenuse is the resultant. Then use Pythagoras. This plus this square root immediately. I don't even need to do composition of velocities. This follows directly from the diagram. And the angle, then I will not make the mistake of thinking that the angle is 57. Now I can see that the angle is given by the tangent of theta being the opposite, which is the velocity of the water with respect to the shore, in other words, the velocity of the river. And the vertical is going to be what? is going to be the adjacent is going to be what the velocity of the boat with respect to the water, which again is given as 1.85. And if I have that, then I just quickly solve for theta, and I just find that theta is about 33 degrees. I don't care about the decimals in here. But this is another example. You can use the math explicitly, and it works always. Sometimes it's much more elaborated than actually using the vectors and solving with the vectors trivially, because this is pretty simple. So Katoa and Pythagoras theorem. So in relativity, many of these problems are solved easily like that, and you don't even need to know all this composition of velocities, right? It's sort of a geometrical effect. And that's all there is in reality. But if you don't know, you go through all the steps. Just make sure that you always understand that the math is telling you something with respect to the physics that you have defined. So you have to translate, so to speak, the math result into the physics of the problem. And so you understand that this is not anymore the elevation over, this is the elevation, over the x angle, over the x-axis, over the vertical, but that's not what they're asking for. If we're asking for, or that's what they're asking for, but 57 is not well defined here. 57 should be actually from 0 to 90 plus 90 to 90 minus 57, right? So it's 180, which is the flat angle, minus 57. So actually the angle, if we use the traditional definition, should be 180 minus 57, which is elevation over the x-axis. I take my the velocity of the boat with respect to the shore, and how much do I have to elevate it to reach that vector? Well, I have to go all the way up to 90, and then I have to keep going 33. What I have solved for is actually this 57, which goes from here to this. But the elevation is this, not defined like this, right? So that's why it's important to understand what are the concepts that you're working with. Try to make a diagram always to begin with. You see the difficulties if you don't, because when you do the diagram, it becomes trivial trigonometry, so Katoa and Pythagoras. If you don't, then you're going to start doing these things, and even if you do them, in the previous example we had no much trouble, but now we have room for error, because if we say the direction is 57 degrees, that's not true. If you go by the radio to the boat and say, oh, your vector is 57 degrees, right? You have to go towards 57. What's this guy is going to do? This guy is going to be pointing 57 degrees, because this is what we typically understand as 57, and that's not what you want. What you want to tell him is just, don't do 57. You have to do now 123 degrees, because that's actually what's going to take him 90 and 123, and that's going to be the vector which is parallel to the one that he actually needs to take. So that's the important thing to bear in mind. We could also translate this 33, actually, that's not the problem, right? Once we realize it's 33 plus 90, and that's 123, obviously, it's the same. So again, it's faster. At the end of the day, you need to understand what you're defining. If you define the direction as the elevation over the x-axis pointing positive, align your vector and rotate it until it points where it's actually pointing, and that's what we define as the direction. These angles are useful in finding the actual direction, but if you express them just as 33 or as 57, they're not really telling the entire story. If you tell the guy, oh, the direction is 33, it's even going to be worse, right? Because it's going to be 33. So he's going to be just pointing that direction. That doesn't help, right? So that's one thing. Now, part B is actually just taking this result that we obtained and finding out how long it takes to cover the distance. So based on this, we can actually solve then a problem in kinematics. Now, in part B, they're asking us how long does it take to cover the 110 meters width of the river, right? So this is D, which is 110 meters. Now, we cannot forget the previous results and the previous information that we learned in kinematics. And what was that? That when we're moving into dimensions, motions can be and have to be decomposed. So this will be the equivalent of saying I have a parabolic shot. How long does it take to touch the ground is irrelevant. It's independent of how much horizontal velocity I have. If I throw the object upwards or I throw the object towards the side, provided they both have the same vertical component, they both are going to touch the ground at the same time. One will go up and down while the other one goes like this. But they both touch the ground at the same time. So this is the same. What is going to be determining the time it takes you to cover the river is actually going to be the velocity in the direction perpendicular to the river. And so what direction is that in our diagram? Well, that's just simply the velocity of the boat with respect to the water, right? So that is going to be the velocity of the vertical of the of the velocity. So now we know we could write the equations. We can do it quickly. Let's say that this is y. The y final is 110. The y sub 0 is how much? 0. We can take it as 0. What is the initial velocity on the final velocity in y? We don't know. Let's say the initial velocity Well, the initial velocity is going to be just the velocity of the boat with respect to the water. And how much is the acceleration? Acceleration, so this is 0. And once we know that's just simply the same as the velocity of the boat in water. How much was the velocity of the boat in water? We just solved for that. That was 185 meters per second. And so it just becomes trivially saying, how long does it take? Well, you can use any equation. So one equation we could use is just simply actually the definition, right? So we can use the change of y is equal to final velocity plus initial divided by 2 times time. How much is this? The velocity is constant, so average velocity is obviously the same as the velocity. So VW, this is V, which is W, this is 0, which is VW. So twice VW. So actually, how much is the time? Well, that's going to be the change in y over velocity of y, of the boat in water. And how much is that? Well, time is going to be 110 meters divided by 1.85 meters. And if you solve this, it's about 59.5 seconds. So 59.5 seconds. So time it takes is 59.5 seconds. Okay, the next question is this 59. So the next question becomes, and then how far it will reach in the x position. Again, remember, we're moving in the negative direction. So whenever we finish this calculation, let's not forget to put the minus if the minus doesn't appear there, or directly just use the equation. So basically now we're going to ask, what is it when this is 59.5? So we could do the same thing here, and then start identify. What's the final position? We don't know. What's the initial position? Let's take it at 0. What's the x velocity? Well, the x velocity, we don't know. What's the initial x velocity? Well, the initial x velocity is just simply the x component of the boat with respect to the shore, which is just pretty much the velocity of the river. So that's minus 1.2, which is the velocity of the water with respect to the shore, which is minus 1.2 meters per second, right? And how much is the acceleration? 0. The boat is not working. It's just, it's just rowing with constant velocity, so there's no acceleration. So then it becomes also minus 1.2. And how long does it take? 59.5, which is got this time. Again, it's an example where the time is the connecting piece, this vertical and horizontal decomposition that we make always into dimensions. And then the question is, how much is delta x? Well, we could use actually the same thing, and then just realize the delta x is minus 1.2 plus minus 1.2 divided by 2, which of course this is minus 1.2, and times 59.5 seconds. And if we multiply that, we're going to find that the change in horizontal position is 71 meters negative. What does that mean? Is actually what we expected. We're going from 0, and if this is the x positive, we're going from 0 to all the way up to 71 meters. If you end up having a positive number, double check, make sure you've made a mistake, then realize if you have defined the displacement properly as final minus initial or initial minus final. In this case, what we're saying is the final position minus initial is minus 71, so final position initial, final position, just solve for final position is going to be minus 71, which is exactly what we expect. Otherwise, it would be weird, right? If we're going in this direction and we end up there, that would be weird. So that's the solution, and we see how we can compose velocities, how can we translate systems, and find the solutions to our kinematic problems. So problem 4 in discussion is a pretty interesting example. Let's say that there is a street, right, and there's a car that is moving with 40 kilometers per hour. They also tell us not to make mistakes, that that's 11.1 meters per second. And there's another car that is moving also with 40 kilometers per hour. And so the question here is, what is the relative velocity of one car with respect to the other? For instance, determine the velocity of car 1 as seen in car 2. So using our notation, we want to find the velocity of 1 on 2, right? Now we know, of course, the velocity of 1 on 2. We know that the velocity of 1 on 2 it's equal to the velocity of 2 on 1 with a negative sign, right? This guy is going to see this guy going towards him, but this guy is kind of seeing this guy going towards him in the opposite direction, right? Again, you can think about these things to see them. Anyway, the question is how much is v12, and so obviously this doesn't tell us much, but we can say, okay, let's just use the composition of velocities. How do we do that? Okay, so we see that velocity of 1 on 2 is going to be equal to the velocity of what? Well, this is car, let's say this is car 1, and then let's say that this is car 2, okay? This is car number 2. Oh, sorry, number 2. So, how much is velocity of 1 and 2? It's the same as velocity. What's the object I'm identifying? The object is 1. and I'm going to say, excuse me, I'm going to end up having here, well, this is the velocity of 1 with respect to 1 plus the velocity of 1 with respect to 2. What's the velocity of 1 with respect to itself? 0. No object moves with respect to itself, right? Can you move with respect to yourself? No. I mean, unless you're dreaming or having one of those acid trips, you actually do not move extracorporeally, right? That doesn't make sense. In physics, 0. We cannot analyze that sort of thing. And what is the velocity of 1 and 2? Well, that's exactly the velocity of 1 and 2. This is trivial. So we didn't say anything here, right? So the other, the other option would have been what happened if we had said, I mean, we cannot get information from this composition of velocities. If we try the reverse, it's gonna also be something irrelevant. It's just a truism, right? So what do we do in this case? Well, this is when we go back to this idea of the river, we could define a third frame of reference. And in fact, it might be interesting to just, obviously these are in route for collision, right? That's going to be probably the collision because they're both traveling at the same speed. If they're the same distance, they're going to hit there. And then we can say, okay, what if I define a frame of reference here? That's this frame of reference. And then I can imagine there is a manhole or something in there. There's a small portion of the pavement or something. I'll take that grain of pavement, whatever that is, asphalt, and I just define my frame of reference. And then I can just define this motion here and this and this. And why is that important? Because then I can say that the velocity of 1 and 2 is actually is equal to the velocity of 1 on 3 plus the velocity of 3 with respect to 2. So 3 and 3 will cancel and I will end up 1 with 2, which is what I want to do. This I can do. So then I can just identify, okay, let's see, what's the velocity of 1 in 3? Well, what's the velocity of 1 with respect to 3? This is car 1, it's moving with respect to 3. So with respect to this one, how is the car moving? Well, it's moving with purely horizontal velocity of 11.1 meters per second, no vertical component. Simple. What is the velocity of 3 with respect to 2? Which in other words is, how is this asphalt moving with respect to the car? Well, you would say the car is moving with respect to the asphalt, but the other way. The asphalt is moving with respect to the car. So if the car is moving with respect to the asphalt upwards, the asphalt is moving with respect to the car downwards. So 3,2 is the same as velocity of 2 with respect to 3. And then we can say that was the velocity of 2 with respect to 3. In other words, how is 2 moving with respect to 3? Well, it's moving with positive y direction, 11.1. So how much is minus 2.3? Right? So that's going to be 0 minus 11.1. And so I got both velocities, and then I just can compose them. So how do I describe velocity of object 1 with respect to 2? That's going to be equal to 11.1 here, 11.10 plus this one, 0 minus 11.1. So how much is that? 11.1 minus 11.1. Let's look at this and see if it makes sense. Velocity of 1 with respect to 2. What is this object doing? Well, it's moving this way, but it's also moving. If this guy is approaching this guy, just take this guy and put it here. It's approaching this guy, right? So from the point of view, if you take the point of view of car 1, car 2 is coming to him. If you take the position of car 1 in 2, that is to say, if you take the point of reference of 2, then car 1 is actually coming to you, and it's actually coming to you with negative component. So it's coming towards you, towards the positive component. If you're in number 2, you see this guy coming here, so positive x, but it's also coming downwards because it's coming to you, 11.1. Why is it coming to you? Because you're going to him. So again, conversion, right? So this makes plenty of sense. And now, of course, if the question is determine the velocity as the answer, you could get, excuse me, from here the solution of how much is the magnitude of that velocity, and that's just going to be simply 11.1 squared. Okay, let's do it. 11.1 squared plus 11.1 squared, and of course that's the square root of 2 of 11.1, which is 1.4 something, right, times 11. Let's see if we have a solution here, which is 15.7 meters per second. And if you were to know the angle, well, you can do actually the number, which is just saying, again, draw the vector. Let's come and draw the vector. Now we're in point of reference 2, right? We draw our frame of reference, and then we see that we have a vector, what vector? 11.1, right? And 11.1, excuse me, and 11.1, but not up, downwards. So we have velocity of 1 with respect to 2. Draw it. And then you ask yourself, I'm trying to find this, which is the elevation. So how much is that elevation? Then you can use the tangent of theta is what? Opposite. 11.1. Right? Or negative. What's adjacent? 1 horizontal. So how much is this minus 1? So how much is the inverse? X, then you have the triangle. So negative in theta. We're allowed to do that. Why? 55. And then you see that this is 115 degrees. You could say or 30, 9, 20, 15, and then you stop there. So this is saying the same. If you don't put the number here negative, just remember to add it later, because at the end of the day you need to make a number that according to your definition of direction makes sense. But this is very interesting. If you see, like in the movies, when there's a crash and a collision, like a collision, right, you see that the car looks like, oh, it's coming to me. And that's actually what appears from your point of view of here. But the same thing, but opposite, happens to the guy here. The guy is going to say, oh, it's coming to me. It's not that it's coming diagonally, it's actually because you are taking yourself as stationary, that guy is approaching with his own velocity, vertical plus the horizontal one, and then we can compose. So this is the velocity of 1 and 2. How much is the velocity of 2 and 1? Well, 2 and 1 is negative. So if this is the vector, how much will be? 2 and 1 is the opposite, is negative, which is taking the same vector, changing the arrowhead, negative vector. So again, that's why it's important to see the vectors, because then these things become trivial. You just have to be careful and understand that you are using mathematics to describe physical situations, but once you get your numbers, make sure that they are reflecting the physical situations and they are defined according to the standard definitions, and more importantly, according to the question that is being asked in the problem. Just a couple of comments final on relativity. Relativity, this is classical relativity, which is composition of velocities, and this is the idea that allows Galileo to compose velocities and say why the objects fall, and then it makes sense that we're saying that the Earth is moving, not only, instead of saying we're fixed and the rest of planets are moving around us, we can say that the Sun is at the center of the Earth, and then the rest of the planets are, moving, right? So this was obviously part of the problem of the Galileo affair, as it's usually called. The other problem, of course, is that he didn't have direct evidence. That happened about 100 years after Galileo died. That's the first time that we had evidence that indeed we could claim we are the ones rotating, or all the planets are rotating around the Sun. The other thing I want to say is that relativity, Galilean relativity, even it's just limited. And it's just limited to velocities much smaller than the speed of light. You might have heard the word relativity before, typically associated with Albert Einstein, special relativity, right, or general relativity, but in general, to the two theories of relativity of Albert Einstein. In particular, the special one is the one that says, how do you compose velocities when you have things moving at high velocities? High velocities meaning velocities approaching the velocity of light in vacuum, which is about 300,000 kilometers per second, right? That's the one. So Galilean relativity works, but it only works for very small velocities, which is typically the ones that we observe in our day-to-day life. If you're going to start using particles moving or objects moving at quasi-luminical velocities, then you have to use other sort of relativity that we will not study in this course. The other thing is relativity is actually still useful. We're seeing it, for instance, to calculate an accident, or seeing if you're in the route of collision of two airplanes, or an airplane and a helicopter or something like that. Then you can use relativity, and then the kinematic equations will tell you, oh, you're in the route of collision. And airplanes and flying devices, and also boats, have this sort of systems where they can calculate when two objects are in a collision trajectory that intersects, which means they're going to collide. And when that happens, of course, it gives them warnings, and then can adjust automatically height and speed and direction and all those things. The second thing is you can find an example of Galilean relativity or classical relativity, for instance, in the case of an accident on the sea. If you call the Coast Guards because your boat is sinking, you typically give the last coordinates of your position, right? You give them your position with respect to the Earth. But the sea is potentially moving. So that as soon as you give them the warning that you just sunk it, let's say in this position, if the river or the sea is moving with a certain flow, then it means that by the time the guys are here, this is the Coast Guards, they need to come here, you're not going to be anymore in here, you're going to be more in here. So the guys in the Coast Guard understand that that's actually the situation, and they don't target your position, they target the position where you should be, and then they go with whatever patterns they do to actually find survivals. But this is a classical example of classical relativity. This is still useful today. So again, when we see theories that supersede on other ones, we say that they're preferred because they cover more, they're more universal in that sense. But it doesn't mean that the other ones are false. It's true, it's just simply that it's limited in the set of applications that we can find. But in our day-to-day life, that's pretty extended, so we're happy with that.